Hi guys, welcome to today's recording. We are going to continue our buffer solution. So this is our part 2. I'm just going to go through some more calculations for buffer. So if you understood everything from the first video, then this is where you want to be, because I will go through some of the more typical type of questions and just go through the well, these ones a little bit harder than what we did in the first video. So this is more like the advanced version. But here it goes, especially question 2. I would like people to pay more attention to, because that's going to be more relevant later on with the titration curve. All right, so let's make a start. So first question, if I want you to calculate the pH when 10 mils of this NH3 is added to 30 mils of this NH4Cl, calculate the pH of the buffer solution. So, you know, it's like I mentioned yesterday, you should be pretty good at identifying the solutions now. So you pretty much have a buffer of NH3 and you have a buffer of NH with the buffer of the conjugate acid with this, which is NH4 plus. Okay, so in order to, so first thing first, just put down the equation. I actually don't like this green. Let's just go back to our black color. So pH equals pKa plus log concentration base divided by the concentration of the acid. Okay, so we see a few numbers already. We have the pKa and we have the two concentrations. So before let's find out what the concentrations are. So the pKa concentration, the base concentration, just gonna move some papers off my desk. The base concentration, which is, so first thing first, you need to identify what this is. This is the base. This NH4 plus is the acid. All right, so the acid always has one more H. That's how you can remember it. So the base concentration was 0.124, but now we have an issue, okay, because we mixed 10 mils with 30 mils. So my concentration has now been diluted by how much? It used to be 10, but now there is a total volume of 40 mils. So out of the 40, 10 mils was my NH3, and therefore it's going to be 0.124 times 0.25. That's what 10 divided by 40 is, which is going to give us, where's my calculator, 0.124 times 0.25, and that's going to give us 0.031 moles per liter. Now for our concentration of the acid, this is going to give us which is the NH4 plus concentration, so that's going to be 0.189 times 30 divided by 40, because it's also diluted. So let's do that, times 3 divided by 4, that's going to be 0.142 moles per liter. Okay, so once you got these two concentrations, you pretty much just substitute into the equation. So pH equals pKa, which is 9.25 plus log the concentration of the base, which is 0.031, divided by the concentration of the acid, and then just do the calculation, and then you should be able to find the answer being 8.59. Okay, very typical type of question, but then there is an extra step which is a dilution factor. If you directly came from part 1 of the buffer questions, then you probably didn't have to worry about the dilution, because that was adding a solid into a solution, and then they specifically said assume there is no change in volume. So if there's no change in volume, there's no dilution. But this one's clearly different. I gave you two solutions. They mixed, the volume has increased. That means the concentration would have decreased because it's diluted. So you need to use the original concentration multiplied by the dilution to figure out what the now concentration is, and then use that concentration to substitute into the equation to do the calculation. I do want to point out because sometimes, now I'm not going to do it here because that's really mathematical. It's not really to do with chemistry, to be honest. I mean, it's just rearranging equations. Sometimes they give you this. Sometimes they give you the pH, and they give you the pKa, and they give you, like, say, one of these, like they could give you, like, say, the base at the acid concentration, ask you to find what the base concentration is. So it's literally just working backwards. You have this, you have this, you have this, so figure out, you know, move this to the other side, so you get a number equals to log base over acid. Then you shift log on your calculator, you shift log whatever this answer is, and then so that's just math. That's not chemistry. Well, that is chemistry, but just manipulating a chemical equation using mathematics. But you know, that just comes through doing a lot of these questions and being able to manipulate that. Again, that's, if you can understand what we're trying to do here, then you should be okay with that part of the question, because that's the chemistry aspect that you should be okay to do. Then mathematically, then you know, it will take me longer just to teach a math component of that, but that's not what I'm here for, here to do chemistry. Okay, so moving on. Now, this is the part I do want to spend more time on. This is the thing that I was mentioning yesterday. When I was adding 10 mils of 0.1 mol per liter sodium hydroxide to 50 mils, I'm just going to make that smaller, just, you know, it's going to bug me, the subscripts. Okay. The CH3COH, I know now it's going to be pretty obvious. We're going to add this. It's pretty obvious that these two things that are highlighted are not acid and base, conjugate acid and base pairs. Okay, so you should be able to identify the sodium hydroxide is a strong acid. Okay, and then the CH3COH is a strong acid, strong base, and then the CH3COH is a weak acid. Okay, so when you mix these two things together, you are going to get a neutralization reaction. Now, they may provide you with the equation, but you don't. I mean, surely you get the things you can do neutralization reaction. I mean, my year 10s can probably do this. If you plus a base with an acid, they neutralize each other. You produce CH3COO minus plus Na plus water, and this is your neutralization reaction. And it's absolute essential that if they don't provide you the equation, I would strongly recommend you to write it down, because this is going to work. You can have my words on this. This is going to work 100% with any of the calculations that's to do with this type of question. This could be a titration curve, could be a buffer calculation, could be any of those two things. You will work 100% of the time. And it, you know, especially when you look at some of the aqueous past exam answers, even looking at the answers as a chemistry teacher, it confuses me. I'm like, what the heck are you doing? Just why are you going the long way? Why are you doing this? Why are you doing that? Just go with the easy route. All right, just go with this. Okay. Now, when you're neutralizing, you got given the moles and the concentration, you got given the volume and the concentration, so you know how many there is. All right, so at the beginning, so this is what I tend to do, and it's very evident that, especially at my school, like if someone does this, it's clearly that someone from my class, because I'm pretty sure I'm the only one in my school that does it, because it's a little bit longer, it takes a little bit more time, but it works. Hey, you know, I'll rather spend 5 minutes to get it right than spending 2 minutes and risking, you know, end up doing something wrong there. So I'll, you know, spend a couple more minutes, make sure you get it right. So at the beginning, so what it means is that before I mixed it together, all right, I know my concentration of my sodium hydroxide is 0.1. I know my volume, which is 10 mils, which is 0.01 liters. So at the beginning, I know my mole of sodium hydroxide, which is going to be 0.001 mole. Okay, so surely everyone can do this. For my CH3COH, same thing. I know my concentration, which is 0.05. I know my volume, which is 0.05. I know my mole, which is just going to be 0.05 times 0.05, which is going to be 0.0025. Okay. Again, that's not too hard, I hope. Okay, so this is before anything has happened, and over here I have 0, and I don't really care about those. All right, sodium and water I'm not interested in. So at the very beginning, I don't have any of the products yet because I haven't mixed them in yet. So in my sodium hydroxide beaker or test tube, I have 0.001 moles of sodium hydroxide molecule sitting there. In my CH3COH, I have this many moles of CH3COH molecules sitting around. So after I mix them, go away. And now after I mix them, after I mix them, this will be 0. Why is that? Because the 0.001 is going to be completely neutralized. I'm going to use, because it's a 1-to-1 mole ratio, because you know how we talked about buffer solution before, if you're adding a strong base to this weak acid, it's going to take one of the weak acid to neutralize a strong base. So it's a 1-to-1 ratio. So I'm spending one of my guys to take out one of you guys. So the CH3COH is going to spend equal molar amount of the sodium hydroxide just to neutralize them. So it's going to sacrifice this many moles of CH3COH to wipe out this many moles of sodium hydroxide. So at the end, I still have 0.0015 moles of soldiers sitting behind. All right, so they're the remaining force. They're still there. Okay, because I had this many at the beginning from this calculation, and I used this many to get rid of the sodium hydroxide to get rid of it. So it's now 0. So this is how many moles I have. All right. Now let's go back here. So I spend, now this is going back to the mole ratio stuff before. Maybe I should get rid of this so you can see. If I made 0.001 mole, if I use 0.001 mole of that, and then that's completely gone, surely that makes sense that I made 0.001 mole of that, because for every 1 mole of sodium hydroxide that I neutralized, I make equal moles of the CH3COO minus. So the CH3COO minus, the mole amount, the CH3COO minus is going to be 0.001. And now you can see we have, in our hands some species. One is the CH3COH, which is a weak acid. One is the CH3COO minus, which is a conjugate base. We know this mole, we know this mole. And how do we calculate the pH of a buffer solution again? It's pH equals pKa plus log the concentration of the base divided by the concentration of the acid. Okay, so this is more, so because once you've done that, you know the mole. If you know the mole and they are in the same solution, so you can see that here I have 60 mils, here I have 10 mils, 50 mils, so altogether I have 60 mils of stuff. But mathematically, this is what I'm going to do. I'm going to substitute the pK. Where's the pK? pK is 4.76. So 4.76 plus log. Now make sure you know which one's the base. All right, so this thing is a base because the CH3COOH is clearly the conjugate acid, is a weak acid. So I'm going to use 0.001, which is this number, as my base, divided by 0.0015. Now, mathematically, it's all going to give me the same answer, but just to be chemically correct, because using the equation, I'm supposed to use concentration. Yeah, because that's what the square brackets are for. If you look at the square brackets around B and A, that means the concentration. But what is this 0.0015 and what is this 0.001? These are moles. Okay, so if I want to be really correct, I'm going to use these moles. Remember, concentration equals N divided by V. So I'm going to use these to divide by the volume, which is 60 mils, which is 0.06, which is going to be 60 mils, which is 0.06. But can you actually see? So mathematically, there's absolutely no need to actually include the bits I just highlighted because you're using them divided by the same number. Okay, so I don't think any of my guys in the past have been punished without even writing the divided by 0.06, because once you got the mole, obviously they're dissolved in the same solution. They are in the same solution, so the volume is going to be the same. So if you want to find the concentration, you're just using the mole value divided by the same volume. So what is the point of that? You can just use this 0.001 and the 0.015 and just do your calculation. So I'm just gonna, I've shown you how it works. I'm just gonna delete that. What is the point? That's just one extra step. Okay, so then you can do the calculation. So which is going to be log 0.01 divided by 0.015, and you log that number, which log, and then plus 4.76, and then the pH will be 4.58. Okay, so this is a very, very important step that you need to fully understand. All right, so we are looking at, and you may go, what about the dilution? What about, you talked about the dilution. I got 10 mils here, I got 15 mils here. Do I need to, what do I do with do I not need to worry about the dilution? No, you don't need to worry about the dilution, because this is not a simple, I talk about the two ways of making a buffer. One is by combining the two solutions together, like the one that we did for question 1. I have my NH3, I have my NH4 plus, I just mix them together, then boom, I have a buffer solution. All right, and then you can just figure out each concentration, do the calculation, then you sort it with the question. But for this particular question, it's a different type. It is a neutralization reaction. So when you putting these two things together, they will neutralize each other. So the strong base, or in other cases a strong acid that you're adding in, they will be completely neutralized, because that's all you're trying to do. You're trying to add a small amount of the strong stuff to neutralize some of the weak stuff, so to produce the conjugate pair of the weak stuff, and then you made a buffer solution. Okay, so that's why you added sodium hydroxide in here. You added sodium hydroxide in here not to dilute or do whatever, you're simply adding it there to neutralize. So that's going to neutralize some of the CH3COOH, and so that's completely gone. So what do you use the volumes for? You use the volume to find the initial mole. You use the volumes and the concentration to find the initial mole of the CH3COOH, and then you have the two together, and then you simply use a big one minus a small one to figure out how many moles of this, in this case, how many moles of the CH3COH you actually have left behind. And then you can look at how many moles of the weak stuff, the conjugate base, in this case, the conjugate base that you have actually produced. And then you know the moles of each, and then you substitute them into this particular equation, and then you're done with this question. And I cannot emphasize enough that it is absolutely essential that you know how to do question 2. You need to rewind back, watch it multiple times, or leave a comments, and or get hold of me if you're someone from my school. I'm more than happy to go over that again. But like I mentioned before, it is absolute paramount that you can do this type of calculation, because when you do buffer calculation in a titration curve, this is going to ace any question that comes your way. You can do any part of the titration curve question if you know how to do this question. Because if you think about what titration is adding, with acids and base titrations, you add, like say if I'm a base in the burette, you're adding acid, you're having acid in the pipette, in the flask. You can see that slowly you're adding you're adding a base into the acid, and what are you doing? You're neutralizing them. What if one of them is a strong stuff, one of them is a weak stuff? You are doing exactly what we're doing in question number 2, and you can literally find out the pH after every single drop of the base have gone in, using the step that we just talked about. Okay, so hopefully, this one's not going to be as long. Just want to show you some examples of the pH calculations for buffer, but trust me, just write it out like this. When you see this clearly, very clearly, not an example of simply mixing an acid and its conjugate base, or base and its conjugate acid together. When it's not one of those, because you don't tend to get a lot of them anyway, because those are a lot easier. When you get questions like this, which you guarantee will have in the exams, you just need to make sure that you write down the neutralization reaction, you can figure out the moles of each of them beforehand, you minus them to figure out how many moles you have left over, you figure out how many moles you have produced, which is going to be the equal amount of moles, in this case as the sodium hydroxide, substitute into the equation, and you prepare to get a lot of text for your question, for your answer. Okay, so hopefully this has been helpful. And then next time I'm going to do some titration curve stuff, which is going to be very, very helpful, I hope, because that's tend to be the most difficult part of this unit. Okay, so hopefully you guys got something out of this lesson. Like and subscribe if you haven't done so, and I'll see you guys next time. Bye bye.